We're now going to take a look at a third and final method for finding volumes of solids of revolution using what's called the shell method. First of all, we're going to revisit a problem using the methods that we already know, the disk and the washer methods, and see why we might need a third method. The problem I'd like to investigate is to rotate the region bounded by y equals x squared plus 1, the y-axis, the x-axis, and the line x equals 2. And we're going to rotate this around the y-axis. So let's start by making ourselves a quick little sketch here. Y equals x squared plus 1 is just going to be a parabola shifted up 1. X and y axes are boundaries, and then the line x equals 2. So my region is this. We want to rotate this around the y-axis, which means that we have to draw rectangles perpendicular to the y-axis, or in other words, horizontal. Hopefully you're going to start to see the problem here. Oh, excuse me. If I were to draw horizontal rectangles, my representative rectangle on the bottom is going to go from the y-axis to the vertical line. But up here, it's going to go from the parabola to the vertical line. So in order to do this with horizontal rectangles, I'm going to have to do it in two sections. I'm going to have to split it up right here at y equal 1. All right, let's go ahead and run through this. I'll do the top section first. And for the top section, notice that the region is not sitting right on the axis of rotation. So this is going to be a washer method. If I draw my large rectangle from the axis of rotation to the further graph, the vertical line, there's capital R, and my small rectangle from the axis of rotation to the closer graph, that would be little r, and in both cases, the height of each disk is just going to be a little piece of the y-axis, delta y. So let's go ahead and run the washer method for that top section. The volume of a washer and in this particular case, my little list over here, H is delta y, capital R would be just 2, right? Technically 2 minus 0, or just 2. And little r, let's see, we're doing horizontal rectangles, so we would have to have this be an x equals. So I'm going to think of this as, let's see, x squared would be y minus 1, and x would be the square root of y minus 1. Positive square root, since I'm in the first quadrant with positive x values. So that small radius is square root of y minus 1, again, technically minus 0. So the volume of my washer, pi times 2 squared minus the square root of y minus 1 squared times delta y. Volume of the entire solid, once it's rotated, we get by integrating, and that'll be 4. Subtract the quantity, y minus 1. Be careful with the parentheses there. That negative is going to have to distribute. dy. The integral is with respect to y, so we need y values. And that means I am going to need this intersection point. Probably should have gotten that before. But notice if you plug x equals 2 in here, 2 squared plus 1 would be a height of 5 at that intersection point. So we'd go from 1 to 5 for this top region. All right. Let's see. Again, not a difficult integral to do, but I'm just going to tuck it in the calculator real quick, just for speed. Oops, that was a 1 to 5. And we've got 5 minus the quantity. Goodness sakes. 4 minus the quantity. X minus 1. There we go. And I get 8. So I'll actually just get 8 pi here. All right, what about the bottom section? First thing that I'd like you to notice about the bottom section is this section does sit right on the axis of rotation. So we're going to be able to use a disk method here. That means I really only need one rectangle, again perpendicular to the axis of rotation, and drawing it all the way over to the only graph, which is the vertical line. So the volume of a disk, pi r squared h, and in this case, our h is still going to be a delta y, and our radius is always 2. So I'll get pi times 2 squared, delta y. And then the volume of the solid of revolution we'll get by integrating that. That would be 4 dy. And again, y is the variable of integration. That bottom section just goes from 0 to 1. That integral is just 4y. From 0 to 1, which is just going to give us 4. So we'll get 4 pi. All right, my final answer then, when I combine the top where I used the washer method, got 8 pi, with the bottom where I used the disk method and got 4 pi, my total volume is going to be 12 pi. All right, not difficult, doable certainly, but it was kind of a pain to have to use 2 separate techniques, 2 separate integrals in order to get the volume. So we might ask ourselves, perhaps is there a better way? Notice that with this shape, if I had been allowed to do vertical rectangles, I could have gotten the whole shape with just one set of vertical rectangles. The problem is the methods that we've learned so far have required that our rectangles be perpendicular to the axis of rotation. The question we're going to ask ourselves now is there any way to do something so that I could draw my rectangles parallel to the axis of rotation? Let's take a look. And actually, I think before I even go through this, there's a little animation I wanted to show you that does exactly that. Watching this animation for the rectangles going parallel to the axis of rotation. We're doing this shape, and we're going to try and rotate it around the y-axis. And notice they're going to do vertical rectangles, which are parallel to that axis of rotation. Watch what happens. Oops, there we go. They're just showing us splitting this up into several pieces. And there's a representative rectangle. And notice they're now rotating that representative rectangle around the y-axis. They're not generating a disk. They're generating what we're going to call a cylindrical shell. It's like a cylinder that's just been thickened up a little bit. They're now going to do this for a bunch of little rectangles. And they're only going to draw half the shell so you can kind of see inside it. But notice you get these shells that kind of fit one inside the other, comprising an approximation for the volume of the whole thing. They're now filling this in so they can see the complete shells creating this volume. Now, if you did lots and lots of tiny little shells where thickness goes down to infinitesimally small, you would get a nice smooth volume rotated around that y-axis. And there we go. So that is what we're going to try to work with this shell method. All right, so back to our notes. Again, the problem that we just finished doing, what was difficult or at least inconvenient or time-consuming was the fact that you had to do it in two sections. So, again, the question was, is there a more convenient way to do the problem? And this is where we're going with the cylindrical shell method. We start by redrawing our representative rectangle in the vertical position. So that's what they've done right here. This right here is the representative rectangle. Rotating that vertical rectangle around the y-axis created that cylindrical shell. And if we do a whole bunch of them and fit the shells one inside the other, we get an approximation for the full volume. All right, so if we take this vertical rectangle, revolve it around the y-axis, we get the cylindrical shell. That cylindrical shell would kind of look like this. It's a cylinder that's just got some little tiny thickness to it, right? It's not quite completely hollow. It's just a little bit thick. Imagine taking a piece of paper, right, and like kind of rolling it up and creating a tube. That's what we've got, just a tiny little thin shell of a cylinder. Keep in mind that piece of paper that you rolled up to form a tube. And imagine now taking that cylindrical shell, and I want you to cut it vertically. Cut it open. What's it going to look like once you open it up? Well, once you open it back up, you've just got your piece of paper again, right? So it's going to look like this rectangle. Again, it's just a tiny little bit of thickness to it, not much. So technically it's a rectangular prism, or a box. It's just a box that's very, very narrow. If I figured out the volume of that box, that would be the volume of that cylindrical shell. Well, the volume of any box is length times width times height. So here's the length. The width is just this little tiny width, and there's the height. So the length here actually came from the circumference of that circle. And the circumference of a circle is 2 pi r. The width, that's that little tiny piece that originally came from how thick we made our representative rectangle. And that's typically going to be our dx or dy, delta x or delta y. So for now, I'm just going to call it thickness. And the height, notice the height of the rectangle eventually became the height of the cylinder and therefore the height of my box. And that was just my function, right? So ultimately, when I do length times width times height, I'm going to have the length 2 pi r times the height, I'm just going to rearrange the order here, times the width, which is really the thickness. Okay. And that gives us the formula for the volume of a shell. The lateral surface area, this, times the thickness, or 2 pi RH, that's that lateral surface area, length times height, times thickness. And that's what I'll use every time I do a shell method problem. Right, we've seen we have a different formula for each of our methods, right? For the disk, it was pi r squared h. For the washer, it was pi times the quantity r squared minus little r squared h. For the shell, it's going to be 2 pi rh times the thickness. All right, just like before, we can imagine then slicing up a whole bunch of little shells, right? There'd be a bunch of them that we would have to add up, or in other words, integrate, to find the volume of the entire solid. And so we'll integrate 2 pi rh times the thickness between whatever our limits of integration end up being. So let's try this. We're going to go ahead and redo that same problem, the one that we already got an answer of 12 pi for, only this time we're going to do it using this new shell method. See if we come up with the same answer. So once again, I'm looking for the region bounded by y equals x squared plus 1, the y-axis, the x-axis, and the vertical line x equals 2. I'm going to make a quick sketch of this. Parabola shifted up 1. My vertical line, x equals 2. And then the x and y axes forming the other boundaries. And there once again is that region that I want to rotate around the y-axis. Now last time we used our old rule that we had to draw rectangles perpendicular to the axis of rotation. So we drew horizontal rectangles. We're now going to use cylindrical shells, so now I can draw my rectangles parallel to the axis of rotation. So I could draw a representative rectangle this way. And of course, what's really nice about that is the fact that that same rectangle really is representative no matter where I draw it. It's always going to go from the x-axis to the parabola every single time. So I only have to set this up once. I don't have to subdivide my region. All right, so just a reminder, the volume of the shells was 2 pi rh times the thickness. I'll just abbreviate that with a th. And the thickness is fairly easy to identify. That's just how wide my little rectangle here is. Thickness in this case is a little piece of the x-axis. So I'm going to use delta x for my thickness. I also need to identify the R and the H. Now the radius is going to be the radius of the cylinder that gets generated when you revolve this rectangle around the y-axis. So the radius would actually go from the y-axis to that little rectangle. That radius becomes the radius of the circle when you rotate. So in this case, that radius goes from 0 to whatever x value I happen to be at here. My radius is just x. The height is going to be the height of the rectangle, which in this case would just be x squared plus 1. Technically, I'd be subtracting 0 on the bottom, so I won't bother writing it. So the volume of a shell, 2 pi, radius of x, height of x squared plus 1, thickness delta x. In order to get the volume of the whole solid then, I'm going to integrate, and I'm going to pull that 2 pi out of the integral. That leaves x squared plus 1 dx. And this is an x integral, so my x values would go from 0 to 2. And I'm going to go ahead and integrate this one by hand again. I do have to multiply this out in order to do it by hand. Let's see here, what have I got? That would be a 1/4 x to the 4th plus 1/2 x squared from 0 to 2. That'd be 1/4 times 2 to the 4th is 16, plus 1/2 times 2 squared is 4, minus when I plug in 0, everything just becomes 0. It's 4 plus 2 would be 6, and there it is again. There's that 12 pi. Same answer as we got last time, but notice this time I could do it all with just one integral. So that's our shell method. The shell method is useful when, for whatever reason, you really don't want to draw your rectangles perpendicular to your axis of rotation. For whatever reason, it works out better in the particular problem you're doing to draw them parallel to the axis of rotation. That's when you want to use the shell method. So let's go ahead and just kind of do a little quick general sheet on that, since this is pretty different from the disc and washer. Just a reminder again, when we draw our representative rectangle for the shell method, it's always going to be parallel to the axis of rotation. The height of the rectangle will just be the height of the shell, that's our h, and the base of the rectangle is the thickness of the shell, either delta x or delta y, depending on which way we've drawn it. To draw the radius r, we'll always draw it from the axis of rotation over to the representative rectangle. And that'll give us our circumference, the 2 pi r. So this is another drawing tip here. All right. Let's first of all talk about doing a shell method if we were rotating around the x-axis. So if I've got my region here, and I want to rotate around the x-axis, that means I have to draw my rectangle parallel to the x-axis. So it would look like, oh boy, I drew, no, it's all right. You know what, let me do me a favor. I'm going to actually go ahead and I'm going to draw this as more of a function here. X equals f of y. I want that to have a non-constant. We would be able to say then that drawing our rectangle parallel to the axis of rotation would give me a thickness, delta y. The height of my shell is actually going to be the length of that rectangle, which I could actually have another function over here. Let me do this a little bit more generally. Let me call that g of y. We could have a f of y minus g of y, right minus left. The radius of my shell, to get the radius, we always draw from the axis of rotation to the rectangle itself. Notice that's going to be the y value this time. So the circumference of the shell, actually, you know what? Let's just not even do that. The volume of the shell then, we said was 2 pi RH times the thickness. So we're going to get 2 pi times the radius, which is y, times the height of the shell, f of y minus g of y, times the thickness, delta y. And then if we use an integral to add these all up, we can pull the 2 pi out of the integral. Like so, between whatever y values, a and b, we happen to be working with. All right, let's go ahead and draw a general scenario for rotating around the y-axis. Okay. This time, I'm going to have a y equals f of x and a y equals g of x. Between a and b. And so here is my region. And my goal is to rotate around the y-axis. Okay. So once again, with the shell method, we always want to draw our rectangles parallel to the axis of rotation. So I'm going to draw my rectangle vertically this time, meaning the thickness of the shell is going to be a little piece in the x direction, delta x. The height of the shell, I'm thinking top minus bottom here, so f of x minus g of x. And the radius of the shell, to do a radius, you always go from the axis of rotation to the rectangle. So my radius this time is going to be whatever x value we happen to be at. So this is x. And again, I was doing this a little differently. Let's just go ahead and write down the volume of the shell. Two pi RH times the thickness. 2 pi times x times f of x minus g of x times delta x. We can then integrate to get the volume of the entire solid, pulling the 2 pi out of the integral. It'll just look like this. All right, so that's just sort of some generalities, kind of a reference sheet, if you will, that you might want to use as you're doing these problems. Let's get to some examples. So here's example 2. We would like to find the volume generated when this shape, which is actually graphed for us right over here, is revolved around the y-axis. And here's even a little picture. If you took this and revolved it around the y-axis, you might get something that looks about like that. All right, our question is, which is the better choice, the washer method or the shell method? I know that my region here does not sit on the axis of rotation, so I know it's not going to be disk. It'll either be washer or shell. Let's think through those two options. If I was going to try a washer method on this, for the washer method, we know that the rectangles have to be perpendicular to the axis of rotation. So that means they'd have to be horizontal. Is that a good choice for me? Well, if I have horizontal rectangles, I would have to solve this for x, because the length of that rectangle would be the right side minus the left side. I'd have to have this x value minus that x value. Is this an easy equation to solve for x? Absolutely not, right? I've got both an x squared and an x in here. I'd have to complete the square. Nothing I really want to do, so ouch. Not very appealing. What if I choose instead the shell method? With the shell method, we draw our rectangles parallel to our axis of rotation. So now I could draw my rectangles vertically. Because I'm drawing my rectangles vertically, the height would just be the top, or y value, minus 0, and I can leave this solved for y. That's certainly a much better choice, unless I really love to complete the square and play around with a lot of algebra. So we're going to choose the shell method so that we don't have to solve for x. Let's do it. All right, so here comes our shell method. I've kind of drawn this out for us this first time so we can really see where we're going. Here's our representative rectangle right here. And I'm just going to kind of repeat that over here. We imagine taking that representative rectangle, rotating it all the way around to form our cylindrical shell, which is what's illustrated over here. Generally, though, I won't draw that for us. We'll just work straight from the representative rectangle. All right, we know that we need the thickness, the radius, and the height so that we can figure out the volume of our shell. And the thickness in this case is just going to be that little piece of the x-axis right here. So the thickness is going to be a delta x. The radius, since we're going around the y-axis, we always go from the axis of rotation to the rectangle. That's my radius. That's a horizontal distance. That's x. The height is the height of my rectangle, and that would just be the y value here, negative 4/9 times x squared minus 10x plus 16. So we've got everything we need. The volume of the shell, 2 pi RH, times the thickness, 2 pi times the r, which is x, times this height, and the thickness delta x. All right, I think we've got everything we need. That means that we can integrate to find the volume of the entire solid. And I'm actually going to pull all of this out. I'm going to pull out a negative 8/9 pi. And then my integral just has the x times x squared minus 10x plus 16. I often use that trick of pulling out all the constants. It just means less typing into the calculator for me. All right, this is an x integral. And I can see up here, just barely, on my picture is still on screen, the x values seem to go from 2 to 8. We'll take that from the graph that they gave us this time, although of course we could have also factored this to see that same thing. All right, doing this in the calculator, I got negative 180 for the value of that integral. And so, looks like I'm going to get a positive 160 pi for a final answer. All right, let's try a few more of these. In example 3, we'd like to rotate the area bounded by y equals x cubed plus x equals 2, and the x-axis around the line x equals negative 2. And we'll calculate the volume using this shell method. Let's go ahead and get a graph of this first. I actually kind of pre-graphed this one for us in Desmos. It's right here. There's that x cubed plus x. And there's the vertical line x equals 2. And then the x-axis was the third boundary. So that would be down here. So you can kind of see this almost triangular shaped region just with a little curve to it, right, would be what we'd be looking at. That intersection point right there is 210. So I'm going to make a little sketch of this. And then the x-axis rather forms the other piece of the boundary. So here's my region. All right, we want to rotate this around the line x equals negative 2. So let me put that in there. Axis of rotation. And since we are going to use cylindrical shells, we're going to draw our rectangle parallel to that axis of rotation. So we want to draw them vertically. Notice this is a very good thing because by drawing vertical rectangles, I can leave this solved for y. I would not want to have to solve that for x. In fact, I don't think I could. All right, so we're going to go ahead and set up our shell method. We know for the shell method we need the thickness, the radius, and the height. Thickness here is a little piece of the x-axis, so delta x. Watch out for the radius on this one. The radius goes from the axis of rotation to the rectangle. So the radius isn't just the x value, which would be over here. It's actually the x value minus a negative 2. Think right minus left. The x value where the rectangle is located minus negative 2, or x plus 2. And that's that right minus left again. All right, what about the height? The height would be the height of the rectangle. That's going to be that x cubed plus x on top, and it's just 0 on the bottom. So just x cubed plus x, technically minus 0, but we don't have to bother writing that. All right, so the volume of our shell, 2 pi RH times the thickness, will be 2 pi times x plus 2 for the radius, x cubed plus x for the height, delta x for the thickness. To get the volume of the whole solid, we will integrate that. I'm going to pull out the 2 pi. Delta x becomes infinitesimally small, becomes dx. This is an x integral, so I want x values for my limits of integration. That would start from 0 and end at 2. When I did that integral on my calculator, I got 316 over 15. And if I multiply that by 2 pi, 2 times 316 is 632 pi over 15. Okay, so there's one complete shell method problem, start to finish. All right, we've got 2 more here. Example 4 and strangely enough, example 6. So apparently I didn't number very well this time, but you're not missing anything. I just misnumbered. So here's 4. This time we want the volume generated by rotating the area bounded by y equals the square root of x and y equals x cubed about the x-axis, again using the shell method. Let's generate for ourselves a quick little graph here. Let's see, I just want y equals x cubed for one of them, and then y equals the square root of x for this one. There we go, it's this tiny little space down here. I won't bother changing my window, we can see it, and that intersection point is 1, 1. So I'll draw it bigger over here. Y equals x, let's do 1, 2, 3, 4, let's call this 1. Y equals x cubed was like that. And then y equals the square root of x was like this. And we want to rotate this little sliver in here. And we want to rotate this around the x-axis. With that point 1, 1 being the intersection point. Okay, once again, if we're going to use the shell method like we're being asked to use, if our axis of rotation is the x-axis, we have to draw rectangles parallel to that, so they have to be horizontal. So there would be a representative rectangle. Since I'm using horizontal rectangles, I know already I'm going to have to solve for x here, so I might as well just go ahead and do that. This will become x equals the cubed root of y. And this will become x equals y squared. All right. To do the shell method, I need thickness, I need radius, and I need height. The thickness this time is a little piece in the y direction, so it will be a delta y. Radius going from my axis of rotation, the x-axis, to that rectangle. The radius this time is just the height of the rectangle here, or excuse me, how far up the y-axis it is. The radius is a vertical or y value. And then the height is actually the length of this rectangle. Right side minus left side. The right side is this cube graph, x equals the cube root of y. And the left side was on the square root graph, which is now x equals y squared. So the volume of my shell, 2 pi RH times the thickness, will be 2 pi times y times cube root of y minus y squared for height, delta y for thickness. And I haven't said this for a little while. I'm going to repeat myself, but it's been a while since we've said it. At this stage, a good double check on yourself. Make sure all of your variables here are the same. If you ever have a mixture of x's and y's at this stage, something has gone wrong. You've probably forgotten to solve your equation for the correct variable up here. So just a good place to check that. All right. The entire volume then I get by integrating. Pull out the 2 pi. And let's see, these are y values. Now it doesn't really matter since it's 0 to 1 either way, but I am looking at the y values going from 0 to 1 when I select my limits of integration. When I did this integral on the calculator this time, I did not get any nice values. What I actually ended up with was 0.17857. And since that did not convert to a nice fraction, I just went ahead and multiplied this all out on my calculator and got an answer of approximately 1.122. We'll weighty equals for approximate. All right, last example. My weird skipped numbering system here is actually 6, but really it should be 5. And notice we've got the same region bounded by the square root of x and x cubed. But this time we want to revolve this thing around the line y equals 2. So let me just recreate the same picture we had here a couple minutes ago. And there's my region again. This time our axis of rotation is y equals 2, the horizontal line up here at height 2. And we want to rotate around that line. Now it's still a horizontal line, and since we're doing shells, we still want to be parallel to that axis of rotation. So we're continuing to draw horizontal representative rectangles. So to do shells, I once again need a thickness, a radius, and a height. Thickness, little piece here is in the y direction, so delta y. All of this combined tells me I still need these solved for x, so x is a function of y, so I'm going to go back to that. X was the cube root of y, and x is y squared. All right, it's the radius this time that we're going to have to be a bit careful with. Radius goes from the axis of rotation to the rectangle. Now this does not go all the way down to the axis, so I can't just call it y this time. I'm going to have to think top minus bottom. The top of that radius is up here at 2, and the bottom is at whatever y value I drew the rectangle at. So the y value itself would be down here. I've got 2 minus that y value for my radius. The height, just like last time, is actually the length of this rectangle, right minus left, and the right is the cube root of y, minus the left, which is y squared. All right, so the volume of my shell is going to be 2 pi times that radius, 2 minus y, times the height, cube root y minus y squared, and then finally the thickness, delta y. The entire solid would have a volume of 2 pi times the integral of all of this, and again it's a dy integral, so my limits of integration would be from y equals 0 up here to y equals 1. I put that whole integral into my calculator, and again it did not come out to anything recognizable, not a nice fraction or anything. I got about 0.65476. And then I just went ahead and multiplied that by 2 pi to get a numerical approximation to the final answer, and it came out 4.114. All right, that brings us to the end of section 6.4, our third and final method for finding volumes of solids of revolution.